All right, so we're going to continue here on our discussion of the constant strain 2D triangle. Okay, so last time a couple lectures ago, we talked about and introduced the constant strain triangle, and we talked about how there are 6 degrees of freedom per node because there are 3 nodes, and each one of those can move in the x or the y, right? So that would be 6 degrees of freedom per node. And that's represented here by the local displacement vector 1 to 6. We also talked about how these counters can be used. Q 2j minus 1 to Q 2 times j can be used to store two-dimensional data. You can also do this in 3D, by the way. You can use it to do two-dimensional data and store it in a one-dimensional array. And so by using the right for loop, for example, if you loop on j, and j goes 1 to the number of nodes, but then within that loop you're grabbing the x value using this counter and grabbing the y value with this counter, you can, as you loop over one node, like I is equal to 1, you'll have the x and y for node 1. Okay, within one loop. So it's very convenient, and this also works in 3D. So this is a great way in computer science to store your multidimensional data in a one-dimensional vector. Okay, and this is really important because in multidimensional arrays in computer science can be tricky to handle. You know, it's very easy to use in MATLAB. You can do it very easy in C++ or C, but so when it comes to dynamic allocation of those vectors, I'm not sure if many of you know about that, but that's a whole other term in computer science. When you're writing these fine element codes, right, they're using some of the best stuff in computer science and tools because it's high performance computing, but multidimensional arrays can cause trouble. At least that's been in my experience. And so vectors seem to be the fastest way to deal with information. All right, so the shape functions, they're the 2D version of the linear shape functions that we looked at for the trusses. So instead of just a line like we had for the one-dimensional truss, it's actually a plane. So you can see underlying, so we have our element 1, 2, 3, right? That's our fine element. And then, you know, in this extra dimension, this height represents the shape function value. So at node 1, n1 is equal to 1. And then it's equal to 0 at the other values. 2 and 3 are the same way. So here is n2 is 1 at node 2, 0 at other places, and same way with node 3. Any linear combination of these shape functions also represents a plane surface. So as you add them up, it also represents a plane. In particular, n1 plus n2 plus n3 represents a plane at a height of 1 at nodes 1, 2, and 3. So if you add those up, there'll be this elevated surface all equal to 1. So it's parallel to that triangle 1, 2, 3, if that makes sense. Now it turns out that for every value of the shape functions, they have to add to 1. Okay, so n1 plus n2 plus n3 is equal to 1, and therefore they're not linearly independent. Only 2 of these are independent. Okay, so what we do is we assign these values. N1 is equal to psi, N2 is equal to eta. So it's this new natural coordinate. Before we only had psi, and we had things like 1 minus psi over 2 and so forth. Here we're introducing another intrinsic variable, eta, and that's assigned to N2. And then what we do is we say, well, you know, any combination of these values, and then N3 is then 1 minus those values. Okay, so we have 2 natural coordinates, and then the third shape function is determined as a function of those. And it's important to realize the similarity with the one-dimensional element. Okay, so remember, in the one-dimensional problem, the x-coordinates, any x-coordinates, like a billion to a million or whatever they are, were mapped to the psi coordinates of -1 to 1, right? And the shape functions were defined as functions of psi. Here in the two-dimensional problem, the x-y coordinates are also mapped to psi and eta coordinates. And the shape functions are defined in terms of those values. So imagine we have this element, 1, 2, 3. It's in 2D. This is a very strange image to look at because for me it makes it look like a three-dimensional shape, but just ignore the middle for a second and just think about this: 1, 2, and 3. Okay, and you're going to pick a point X in the middle at some random point inside that triangle. Okay, so here's our triangle, have a point right here. Well, if you were to connect the vertices to that point, you would split this triangle into 3 different sections, right? You subdivided that element, and you can define some area of that. Okay, and what we would say is that those areas that we create, so A1, A2, and A3, they must add up to the full area of the triangle, right? Full area of the triangle. So we have this equation: A1 plus A2 plus A3 is equal to A. That's fine. Well, it turns out that you can use these values or this point to actually define where or what your shape functions are. That's kind of useful. So for example, n1 is equal to, so if we were given a point, remember we had this in the 1D, we were said, all right, here's a point P along this 1D line, what are the shape functions? And so we had to figure out, we had to use the mapping to determine that. So this is kind of similar in helping us establish that mapping. So you just take A1 divided by A. So n1 is equal to A1 divided by A. And so forth for n2 and n3. So we have these shape functions established using a method like this, for example. Then this actually leads us to, all right, let's now write the isoperimetric representation of the constant strain triangles. And we're going to do that in the next video.